Testing, testing, 1, 2, 3. Hello everyone. Good Monday morning. Welcome to probably your first class of this week, which is another week in the great procession of weeks that comprise your existence. How is everybody this morning? Hopefully you had a good weekend. For my part, I was painting the kitchen all weekend. It's been quite the little project. When we moved into this house, it was the previous occupants smoked heavily inside of the house, and one of the particularly disgusting things about that is that we happened to have our kettle up against one of the walls in the kitchen, and the steam from the kettle was causing nicotine tar to just leach out of the plasterwork in great big brown drips, which I think it was pretty gross. And now, hypothetically speaking, I've applied enough coats of paint and various primers, etc., over top of said nicotine tar to seal it in permanently in such a manner that neither the appearance nor the smell will appear ever in my house again, at least on that particular wall. So, hopefully that all works out. Yes, nicotine tar is pretty gross. If you are a smoker, I don't mean to be offensive to smokers or anything, although it seems like not many people worry about offending smokers these days. It's more just like... I don't know. I just wish the previous occupants had, like, done so outside, rather than, I had to replace the sink because of all the burn marks from cigarettes, and I have yet to replace the floor in the dining room, which has a bunch of burn marks from cigarettes on it as well. So, I feel like among people who smoke, the people who were smoking in this particular house were, particularly lackadaisical, shall we say. And that's even beside the issue of all of the knife marks that I find all over the place. There was a lot of evidence when we moved in of domestic disputes, shall we say, that resulted in something on the order of 30 what appear to be knife marks on the bathroom door, as if someone were stabbing the door to try to get in to stab someone. So, yeah. Over the last couple of years, we have been doing everything we can to try to exorcise the bad juju. Which has been, quite the little project. Anyway, we've got 30 people. I guess there are a bunch of midterms today, too, eh? Cool. Well, anyway, we could just move right along with our lecture material for today. Today we're going to continue on with the topic of classes. Classes, of course, being the sort of the workhorse of the object-oriented programming language is the class. So just to quickly recap, if this is the first time you've seen this material, a class is a mechanism for packaging together information and subroutines. So you have a bunch of variables attached to classes, as well as functions, and the functions act on the data that's contained within the class. And normally, in terms of abstract units, all of the things within an object should let me use a grammatical analogy. So far, when we've been doing functions, we have been doing verbs, right? A function is an action, more or less. Variables have been our nouns. They are the things on which actions are performed, sort of passively. But now we are talking about fully fledged, sort of autonomous objects. We've gone from talking about the inanimate elements of the earth to things capable of action. We are now talking about objects, like things to which actions are, things that are capable of actions is one way of thinking about it. For example, if you were in programming, trying to define a class for cats, cats would have various attributes like size, weight, degree of fluffiness, propensity for purring, these types of things, number of legs. And a cat class would have various actions attached to it as well, such as, scratch, bite, eat, poop, drink, purr, and partially stick their tongue out without realizing it, which is the cutest thing that a cat can do. So, obviously, there's more than one cat in the world. So, by defining a class for cat, we say what a cat is. We associate attributes with actions. And then, once we have derived that theoretical model of what a cat is, we can instantiate that model of cats several times when we want to describe actual physically existing cats. Like my two cats, I would have a cat object named Martin and a cat object named Marimba. Martin would be, larger, Marimba would be smaller, etc., etc. So yeah, that's classes. Oh. Yep. 3 summer courses. Woof. Yeah. You guys do, I don't. Yeah. Well, on the subject of summer school courses, there were a couple more computer science summer school courses that opened up, that are being opened up this semester. They're being run in the summer term. 1MD3 is being run in the spring term, and then I forget what the other two. I think 1DM3 is one of the other ones. And I think like 1XC3, something like that. So, if you'd like to take some more computer science courses during the summer, I applied to teach those courses, so we'll see if I get them. It doesn't really matter unless you're taking the course and you don't like me, because that would just be terrible to have me 2 semesters in a row. But anyway, moving along. So previously we were talking about this point class. So this is a class for a point in Euclidean space, and we're going to do various things with this. We established, it's basically just an x and a y coordinate with a few different very simple Euclidean operations, such as translate and scale relative to the origin, and we have a built-in function for the Pythagorean theorem, which denotes the distance between two points in Euclidean space, because the shortest distance between 2 points is a straight line. So, methods are called using dot notation. You guys should be well familiar with this by this point. The init method is implicitly called when an object is created. Its parameters have to be supplied at object creation. So, init, this is generally speaking where you will be declaring the member attribute, or the member variables, attributes, the variables that are contained within the class. They get defined inside of init. So, here's a question. If we have our point object, what happens if we try to print one? Not printing a particular attribute of one, just printing the object itself. What do you think happens? Topic 8.py. We get main.pointObject at, and then a big old number in hexadecimal. So, just to explain very briefly, this number is the memory address at which the object is, it's the address in memory where you will find the object that we have defined. So, objects, similarly to lists and dictionaries and everything else that you're working with, even functions have memory addresses, it's contained in memory somewhere. So, when we print the object, what we get is this printout of its location, which is fine, but that might not be very useful. It's possible that we want to override this default definition of what string conversion does, so that we can get it to print something more useful. Because that's, of course, what's going on here. The print method automatically invokes the string conversion function, right? So, we can actually override the string conversion function for any class by providing a definition for underscore underscore str underscore underscore. This is like the opening up of a brand new, whole new world, because this is definitely not the only one of these that exists. Def string takes self and no other arguments. Return open plus string convert self.x. Basically, we're just going to have it print out the coordinates in some sort of more or less organized manner. And you notice that we're actually using the string conversion method on the elements, on the attributes of the class. This is totally okay, because the attributes of the class still, they're still aligned with their own data types. Just because they're elements of a class doesn't mean that they are, doesn't mean that their data type isn't, just a plain integer in the case of these guys. So yeah, you can distinguish in your brain between these different, like, the attributes of a class are not of the class type. Objects of the class are of the class type. Anyway, probably I'm belaboring the point. So if we add this simple definition, call the same thing again, you'll see we now get it printing out according to the string that we are returning from this function, which is pretty cool. It turns out that you can actually override many, many, many different things in this manner. For example, you can override the plus operator using __ add. We'll take self and other, and this will be pretty simple. Return a point object that has as its first argument self.x plus other.x, and as the y coordinate self.y plus other.y. So let's just make these something useful so that it'll show up correctly. And then let's see what it does. There you go. So it's now giving us 10, 12, which is, of course, the sum of these guys. So you'll notice, without this definition, plus is not defined. The operation, this plus operation is not automatically defined for classes, right? Because a class is a very general type of thing. You don't, like, the computer can't intuit what you are doing with a class or what you mean by something in a class. You have to provide the definitions for these types of operations. So, but yeah, so we've got all kinds of these things. But that's kind of cool, right? Mm-hmm. Mm-hmm. Yeah, I'm not sure if Curtis is still going after it. It's the way that it kind of works is when a sessional professor teaches a course, they get a certain number of rights. You get the right of first refusal for that course for a certain number of offerings into the future, and like I'm having to like reapply to teach 1MD3 during the summer as well because I've run out of rights of first refusal on 1MD3, so I'm gonna I have to go in. It has to go back into competitive process. So I'm not sure if 1XC3 is back into competition, and Curtis is just going to teach it again, so he's probably going to get it again, and that's the end of that. Or if that course is actually up for grabs. I suppose I could just ask Curtis, but, you know. Yeah. 1JC3. Ha. Well, if you want to learn Haskell. Do the double underscores mean you are redefining a function name just for a specific class? Yes. So the double underscore has a specific usage within class structures in Python. Whenever you have... They call them magic methods, But the more technical, formal way of describing it is we are overriding. This is method overriding. So when you declare a class, regardless as to whether you put it here or not, you are inheriting from a basic Python construct called object. Object contains a number of these sorts of definitions. Basically, it's the framework into which you can plug your classes. It provides all your basic definition needs. Such as the default string conversion. That's a good example. When you define something here, it will pretty much always be overriding some operation, either a function or an operation that's like basic to Python. So in the case, and the interesting thing about this one is, it's in the case of add, formally and technically in the biz, we call addition an infix operator. So it doesn't, like, the symbol for the operation comes between the two things it's operating on, so we call that infix. So you can do the infix operators as well as just regular conversion functions. Could you reiterate why you may want to use this sort of method? Like, what sort of question or style of question? Well, I'm not sure if this story has become legendary yet, but last semester I gave as kind of the final boss question on the final exam a classes question where everybody had to implement checkers, the game of checkers, right? So I had a checkers game class, and you had a two-dimensional array that kept track of the position of the pieces on the board, and you had various methods whereby the student would enter a move, and it would do the move in checkers. Actually, let me see if I have the code kicking around. That might be interesting as a demonstration of what the power of these classes are. Fall 2020. There's not. Yes, it is a directory. I want in the directory. Thank you. Did I put it in here? Well, yeah, maybe I didn't. I can't think of where it is right now. But if you ask Mark nicely, he did a whole YouTube video on like solving that problem live. But yeah, but that's like a good example of where you would use this type of thing, right? When you're talking about the game of checkers, you are implicitly tying a certain number of actions in with a certain amount of information. The information is the state of the board and whose turn it is and that sort of thing, and the actions are moving pieces and capturing pieces and all of that kind of stuff. So, and of course, I've worried everybody that that now the exam is going to be tough. How difficult is the final exam compared to the tests? The final exam is more difficult as compared to the tests. That being said, I haven't actually written the I haven't done out the final exam for this class yet, so we'll just have to see how it shakes out. Could I solve questions requiring classes with general functions / operations? No. If I ask you for a class, you will create a class. Hypothetically, if you're asking that in the philosophical sense, like, is it possible to get around the need for a class? Yes, it is possible to get around the need for a class using more simple constructs. In general, that's true of many things, right? Like, for example, you don't technically need lists if you create, 100 variables and name them sequentially and just use them, according to a naming convention. You can technically not need a list, but it's more convenient to use a list. In the same way, for particular use cases, you don't need a class, but it's more useful to have them. But yeah. But no, if I ask you to write a class on an assignment or a test or an exam and you don't, then you're not going to get any marks. That's just how that works. Yeah. So, yes. So this is pretty much this is a similar type of example, except it's operating on the person class from earlier. A person with the name, self.name, etc., etc. An interesting one that we can do is equality comparison. So, and this is another one that I like to put on tests because it's useful. So, if we want to override the definition of the equals sign operator, which is a test for Boolean equality, then that's also possible as well. In the case of points, that would typically mean comparing the x and y coordinates of 2 points and making sure that if both are the same, then they're the same point, right? So we would return self.x is equal to other.x and self.y is equal to other.y. And, just to demonstrate that that works, if we have a point 1, 2, is x equal to z, and then tell me is y equal to z. Python 3 topic 8.py. There we go. The first one comes out true, the second one comes out false. Bing, bang, boom. Yes. So, again, notice that in our overriding of the default functionality of the double equal sign operator, we are again using double underscores, and, you have to name it exactly in order for this to work. Right? You can't just provide anything in here. It has to match up with some operation that's predefined. And you can look up lists of these things you can override all over the place. Another important thing to note is that when we're overriding the definition of equality, we are only doing so for objects of this class. We are not overriding equality for example, integers, because, in fact, we are using equality as defined for integers within the context of this this method. So, it's like, you can kind of think of it like for somewhere in the depths of the compiler, equality has a list of things, a list of ways that it's defined. This can be thought of as adding one more definition to the list of definitions that equality has for various data types. Oh, is A7 not out yet? Yeah, I'll get that out today. Pardon me. So, classes can be used to create objects and to define new classes by inheritance. Alright, so now we're going to talk about inheritance. I have alluded to inheritance several times already. So, here's where we actually talk about it. I think I'm going to jump ahead a bit and then come back to those. So, what is inheritance? So, inheritance is, in programming, the analogy is with classification in sort of the natural world, or the physical world, or in meat space. So, within the scope of the English language, or it's a lot more general than English, within the scope of the human brain and the manner in which human beings think about things, generally speaking, our brains are giant classification engines. This is what we do natively to think about things, right? It's like, right now, I am sitting in a chair. This particular chair, this physical object which I call a chair, the only relation it has to the relation it has to my mental concept of a chair is the fact that when I look at it, my brain says that's a chair, right? And chair is a general class of things, right? It's a general class of things which share certain properties. All chairs are objects upon which a human being can sit, right? Armchairs are padded chairs that recline, maybe. Office chairs are chairs that swivel, right? And have levers at the bottom where you can adjust the height, generally speaking. So you can take your definition of chair and you can, further classify it as, kitchen or dining table chair or dining chair, office chair, and sofa chair, sitting chair. What did I call it? I don't know. Anyway, living room chair. We generally put different types of chairs in different, parts of a house, so that's why they get named according to the part of the house they're in. But that's sort of, beside the point. They're all chairs. They all fulfill the basic functionality of a chair. But, we further classify them. So, one might say, in the style of object-oriented programming, that a office chair inherits from chair. So office chair, dining room chair, and living room chair all inherit properties from chair. That is to say, all of these types of chairs share the properties that are common to all chairs, right? So, we're going to see how this works. You can extend this analogy. This is very small, so I'll blow it up. You can extend this analogy as like a general hierarchy of abstraction that overarches all things, right? At a certain level, every single object in your house is an object, right? And, the definition of an object, of a material object in this case, might be something that can be interacted with physically, right? So everything in your house can be interacted with physically, so they all share that property, right? You know, going back to the cat analogy, you can think of it in terms of a biological analogy as well. You know, tigers, lions, and house cats are all felines, right? So they all inherit the properties of felines, but they have specific ways that they have specific things that make them different. So this is the idea of inheritance. You know, robin's flower inherits from carnation. Carnation inherits from flower. Flower inherits from plant, and plant inherits from material object. Right? So, let me see if I've lost everybody yet. Oh, going back to equality. Why am I overriding when you are making equality the same as its default function? For the purposes of demonstration, since you are defining a custom return statement there, let's say you were only interested in equality over the x-coordinate, you could do that, right? It's for the purposes of demonstration. So, going back to our point analogy, or our point class, we can define a new, more specific type of point if we call it a colored point. So you can imagine we're now, like, if you've got a graph and we're trying to chart, you know, two different data series on the same chart, it makes sense to use different colors to do the points. You know, have one red, have one blue. In the same way, you could have the points be represented by triangles or circles or squares or whatever, you know, like the basic statistic stuff. So, class, colored point. Colored point is a more specific type of point, so we want to inherit from point. In technical terms, what that means is everything that's in here gets copied and pasted into the new definition without you actually having to copy and paste it. That's your, like, physical interpretation of what's going on here. Well, virtual, anyway. I'm gonna sneeze. I was going to sneeze. I had sneezus interruptus. Anyway. So. When we define a colored point, all we need to define are the specific things that we are adding that differentiates a colored point from a regular point. Again, going back to office chairs, to distinguish an office chair from a regular chair, we would add like a roll around method, right? So, in terms of colored point, we want to add more information to the point and specifically we want to add a variable that tells us what color it is. So, define init self. We still need to define x and y because, you know, x not y not. Because when you create a colored point, you have to also instantiate that information which is attributed to point, right? But now we can add another one, which is color. So self.color is equal to color 0. And then we can invoke the point class's init method using self x0 and why not? We can also, just for the sake of interest, define a method over this, darken, which will make the color dark in the same way that we made people old before. Just self.color is equal to self.color add the string dark. Actually, we want to prepend it, don't we? Dark, whatever the colors is. So you can tell I'm sort of I'm implicitly stating here that the color is going to be stored as a string. So, this is fine. This is good. So now, if we want to define a colored point, 5, 8, and green, a.darken print a. Gonna just hide these bits here. Oh, I forgot a colon. Silly me. There we go. So you can see that although the string conversion function has not been defined within the colored point class, the definition that's being used is this one, the one contained in the class we are inheriting from. That's the whole point of inheritance. So, this is good. However, if we want to be able to see what the what the actual color is, if we want to view the information attributed to the colored point class, then we're going to have to perform an additional overriding of the string conversion function so that the new information is also displayed. So, you'd do something like this. Define string self return point dot string self added. You don't need to string convert it because it's already a string. Plus, like some symbol there, and self.color. So, if we run this again, you can see it's now displaying the new information. Coolio. So, I think I've pretty much covered that. You can see this is actually exactly what I did in the in Get It. Pardon me. Inherited methods may need to be redefined or overridden. The new method can refer to the inherited method using class name and dot notation. So, as one of your colleagues very astutely pointed out, the default functionality of the equality comparison is to just perform equality over all of the defined attributes. And if they all come out the same, then, Bob's your uncle. So, if we leave equality undefined within the colored point class, then basically it will ignore color when determining whether or not 2 points are the same. So it's just a test to see if they're at the same coordinate. Whether that's the way you want things to operate or not, that's kind of up to you as the programmer. Cool. There we go. So, within the context of Python, of course, our object hierarchy, or our class hierarchy, our object is the most basic thing, then point is the next most general thing, and then colored point is the most specific thing. That's the correct way to think about inheritance. Inheritance is it's a hierarchy of abstractness, right? With the most abstract things being at the top of the hierarchy, and the least abstract things being at the bottom of the hierarchy. So, before we move on from here, are there any questions? Give me a thumbs up if you're okay with this so far. Got a thumbs up from Dorian. Excellent. Cool. All right. As with most things with programming, if you don't get it right now, then the best thing that you can do is practice it. Once again, Python Tutor is an extremely useful tool to be able to visualize what's going on with these things. So, anyway. So, we can use type to be able to see, be able to check the type of an object, right? So, if we take the type, in our previous example, if we print the type of X and we print the type of Y, you'll see that we get class main.point. Oh, I meant to do A, actually. Class main.coloredPoint. So this means that you can do equality comparison over the class names, and, you know, you can use that. That's a way that you can use equality comparison to be able to tell in code what type, what an object's underlying class actually is. You can test it. However, it doesn't pick up inheritance very well. So if we test A to see if it's a point, it comes out false because it's not a point. It's a colored point, right? This is not what we want. We want, ideally, what we would like is a way to tell if an object has the attributes of the point class, regardless of whether or not it's defined as a point at the top level, if that makes sense. So, if you use isInstance instead, what that does is it, rather than isInstance a point, rather than just testing to see what the top level class is, it actually tells you all of the, it'll return true if the class that you've specified appears anywhere inside of the class hierarchy that a particular object uses. So it comes out true. Don't worry too much about this. It's kind of abstract. So, we can also, not to confuse you guys too much with only 4 minutes left in class, but you can also inherit from more than one class. So, and this is where the analogy starts to break down a little bit with the sort of physical object analogy. If you have multiple classes and you want a class, like a superclass, that gobbles up all the attributes of more than one other class, then you can you can have multiple inherited. You can inherit multiple classes from any given class. So in this particular example, what we do is we take the color property and we abstract it away from the definition of colored point. The reason that you would want to do this is color is a more general thing than a colored point, right? You can imagine that if we're if we're expanding this geometry to include things like lines and figures as well as points, color is a property that many different types of things can have, right? So it would make sense to take the color property and all of the actions associated with it and pop it out into a separately existing class. You can think of if you think about a paint program, right? If you think about think about in Microsoft Word when you're adding like an image or a chart or something. Like you can add multiple things to a document. The manner in which you can get words to wrap around that object is the same each time. And that's because the word wrap functionality has been abstracted out of those more specific functions in this manner, right? So we define a colored point class, which inherits the properties of both point and color, and that allows us to use it in the same manner as we were using it before, but in a way that abstracts the property color away so that it can be used for other purposes. In this way, color can be inherited in other classes as well. Reusing code through inheritance contributed to the popularity of object-oriented languages. So, I think that's our lecture for today, more or less. If you have any questions, please ask please ask me now if you have any questions, and if not, then I'll let you guys get on with the rest of your Monday. Like and subscribe! If a property is common to multiple classes, then we make it its own class so that we can be used in a more free manner. Yes. What we're talking about here is more of a design principle. We're talking at the level of design principle right now. Generally speaking, how particular things are broken down into classes is not going to be something you need to figure out yourself on a test or an exam or an assignment or anything like that. For the primary reason that if the classes aren't, named somewhat precisely, then the autograder will fail to find them. So, to some degree, the actual organization of the classes needs to be, common to all of the students in the same way that sitting on a chair is common to all chairs. So, in general, the idea is, when we're a very good design principle in programming is separation of concerns and abstraction, right? If something is more abstract, that means it can be used multiply it can be used in multiple places. And if it's been designed, well, then it can be used in multiple places without introducing bugs or additional headaches. So, yeah, basically. Okay, well, that seems to be everything for today. Thank you very much for your time and attention, folks. Good luck! Have fun! Have fun.